Hi fellas, I've had a couple of questions about the wave equation, how it works and what it means, so I'm going to give it a go at explaining. Here's a graph of one single wave, but graphed with two different x-axes. This one here gives us information about wavelength. This one here will give us information about the frequency and also the period as well. Time on the x-axis, distance on the x-axis. Anyway, they both hold information about a particular wave. So what we need to do is have a look at what the wave equation means, and really what it means is it's all about speed, and that's just distance in a certain time period. That's what speed is, it's meters per second, like that. The wave equation does exactly that. We need to find out where the distance is and where the time is, and that's where the interesting part comes into it. Here's a wave. So this wave is propagating in this direction. We'll say, for example, that this is a rope. So the medium that its wave is propagating in is a rope, and it's moving in this direction at some speed, v, meters per second. Now, in order to calculate the speed, you need to find a particular spot. We'll go this particular point here is going to move, the wave front is going to move in this direction. We know, of course, that that particle in the rope simply moves up and down, but the wave energy propagates forward as shown. So in order to work out the speed of the wave propagating, you need to get some particular point on that wave front, like here, and measure how far it's gone in how much time, distance and time, because v equals d over t. For waves, of course, the most useful distance to measure would be the wavelength, and that's this distance here, right? Wavelength in between the crests or the troughs. So if this continued down like so, that is also the wavelength. That much we know from previous lessons, so that should be good. I'll just rub this out. There we go. Now, we've got a distance, so that's pretty convenient. We can put that up here, and the time it takes to move from this point here to this point here is the period of the wave, right? So that would be t. So it's wavelength divided by the period, and that will give us meters and seconds on the bottom using dimensional analysis. That's speed. That's all the wave equation does. There are a couple of other little complications, but basically that's what it does. One of the interesting points is waves propagate through the medium at a fixed speed. So unlike a car, when you're driving, you go a certain distance in a quicker time, you can change your velocity. With waves, the medium dictates the speed. So this one here, those speeds are fixed. And that makes for some interesting physics and mathematics. So with a wave speed, the propagation of the wave being fixed, like so, and we now know that speed is just distance divided by the time, like that, then if this is fixed and the wavelength changes, which it could do, you could get in that rope, you could have a wavelength that does this instead. Interestingly, because it's in that same rope, the speed here and there, V1 equals V2, right? So the speeds are fixed. So if this one here is fixed, then if the speed is fixed and this one changes, then this one here will also have to change in order to maintain the constant velocity. It's to do with the density of the rope in this case, or the thickness of the air, or the water, all sorts of things, whatever the wave is propagating through, but the velocity is fixed. And so if the wavelength changes, the period would also change. And you can see that here, the wavelength changes here. How many of them go past in a certain time is now much shorter than the time it takes for those two peaks to go past, right? So these t's are not the same, and these wavelengths are not the same. But there's one more thing that we need to talk about with these waves as they're propagating through space at some fixed speed, which is determined by the medium. And that is that for that particular wavelength, and that particular period, and a time, and the distance, that v equals lambda on period, like so. Distance over time, we know that's going to be meters per second, like so. There's another form that you can use here, and that's lambda times f. And the reason why that is because the frequency is how many of those periods pass in 1 second. It's per second of the units, that's second to the -1. And that's defined by 1 on the period, like that. That's what the frequency is. So these two things, these two forms, are all you need to know really about the wave equation. And it works for ropes, water waves, light waves, you name it, waves. That's all there is to the wave function.